Welcome to today's lecture, the last lecture of the series on fluid inclusions in minerals. So, we have been discussing about certain issues, certain questions that would arise in the minds of a beginner when he is starting the fluid inclusion work and has just taken up and getting acquainted to seeing fluid inclusions, taking measurements using a microthermometric apparatus and also following up with many different things. To continue on what we were discussing in the last class, that sometimes it would be advisable to have some terms and the way we denote many of the microthermometric parameters, if it could be uniform all across, that becomes convenient. And as there could be many other parameters which come up, but generally these are the ones which are the common ones. And in addition to that, other terms are derived parameters like mole fraction of any of the gaseous phases present in the gas mixture and so on, the isochore and many terminology which are there. Of course, I am not getting into the details of that, and you could refer to this particular paper of Larin Diamond, which came up in 2003 in the Mineralogical Association of Canada short course on fluid inclusions, where many of the commonly used terms are discussed, but those terms generally will not have much of a conflict in any description or any record of the fluid inclusion work, but what generally would matter much would be any kind of confusion arising out the way they are being denoted. Although many of the times the terms are defined before they are being used for the first time, or even there are sometimes in a documentation we can also write by defining or by explaining the abbreviations which are used. Yet I would say that if there are some internationally accepted agreed upon terminologies for the microthermometric parameters, it becomes easier. Okay. So, sometimes there are some terminologies which are used which becomes a little confusing. So, for example, boiling and unmixing. Boiling, as per my understanding, is a situation which corresponds to the coexistence of a liquid and its corresponding or vapor of its same composition. Say water, liquid water and water vapor. So, this is a situation in which one homogeneous liquid is splitting up into a coexistence of liquid and vapor, and we all know that happens on a boiling curve. The temperature pressure conditions corresponding to the boiling curve is a situation where the fluid is boiling, is in equilibrium with its vapor. In many of the cases, what is referred to as boiling, sometimes in case of mixed, say for example, one aqueous carbonic fluid, sometimes the word the boiling is also used to it, but this would strictly correspond to if a homogeneous aqueous carbonic fluid is actually splitting up into two components as an aqueous component and a carbonic component. This strictly corresponds to a phenomena of unmixing, but not boiling, because we know that is happening because of the solvers which is there, and any composition which is coming here and then getting splitted up into two, and that is the process of unmixing. A carbonic liquid can always be in equilibrium with its vapor, and that corresponds to a boiling curve of carbon dioxide as we saw before, or it could be aqueous. But then in case of a mixed system, the use of the word boiling would be misleading, and there it is unmixing which is more appropriate, and also we know that such kind of unmixing has got a very important significance in terms of the transport properties of the mixed aqueous carbonic homogeneous fluid, and also indicating pressure temperature conditions of entrapment, and many very important implications can be made out of this. And often you will see words, the terms is used as bubble point or dew point, where bubble point actually some vapor is actually condensing to liquid, or the opposite of a liquid is getting evaporated or coming to coexisting with this vapor. So, it is essentially I mean a liquid getting into the vapor phase, a liquid entering into its vapor phase, or a vapor getting condensing and getting into its liquid phase. So, here it is a dew point and this is as bubble point, but we know so they may be, because for the diagrams that we saw before, for example, on a typically on a temperature and density plot, we also have this kind of a field where this is the critical point, and we know that this part is the vapor and this part is the liquid, and going from liquid to vapor it will be like dew point, and from vapor to liquid is bubble point. They can be represented on this kind of temperature molar volume or temperature density kind of plot, whereas we know that on a temperature and pressure space, PT space, it would only represent a boiling curve, and that would actually take care of whether any vapor is actually getting into the liquid field, or a liquid is getting into the vapor field, which will be representing the crossover or actually crossing the boiling curve. So, on a PT space it could only be the liquid vapor or the boiling curve, and when we have also kind of just briefly discussed about a situation where there are fluid mixtures. For example, if it is a mixture of water plus carbon dioxide, then we know that they represent a situation which is like as a phase boundary. On the higher pressure temperature side it is one phase, and on the lower side it is two phase. That means it is a one phase homogeneous fluid or liquid. Here it is an aqueous liquid plus carbonic liquid which is split up depending on when it crosses this two phase boundary. So, this also can be translated into a Tx kind of diagram, on which we could also and that is a situation in which they are referred to as the dew point or the bubble point, but there should be more. So, these are some of the points which need to be understood while following the fluid inclusion literature. And then we would also it is also warranted that some of the issues that are unresolved also should be kept in mind. There could be many more, just I could just pick up this a few number of points. Say for example, the coefficient entrapment of pure carbonic and pure aqueous inclusions. We definitely see innumerable such instances where we see that there are pure carbonic and pure aqueous inclusions which coexist in the same grain of the host mineral, a part of the three dimensional network, satisfying the criteria of being primary in the origin, or even if they do occur on a heel crack, they do very much fulfill the criteria of being entrapped together under the same pressure temperature condition. But then phase relationships we always indicate that getting a pure carbonic fluid would be difficult, but then we definitely need to explain them from what kind of special circumstances could be there, so that and a homogeneous fluid, aqueous carbonic fluid, is actually splitted in a way where the carbonic component is pure carbon dioxide or mixed with a little bit of other soluble species like methane, etc., but no water, and the aqueous part will also be pure aqueous without any dissolved carbon dioxide in it. Even though we know that the solvus is an asymmetric solvus, means the solubility if we consider the room temperature solubility, then the solubility of carbon dioxide in water at room temperature is about 2.3 mole%, but the solubility of water in carbon dioxide is not that, even much lower than that. There are certain instances in which it is proposed that so if it happens to be in very high temperature pressure conditions like in a granulate grade metamorphic rock, there the carbon dioxide being pure needs to be definitely needs to be explained, and that is the reason why on many instances they have been suggested to be of much deeper origin as degassing of the mantle, and this kind of hypothesis were proposed in case of many of the granulate belts in the world, including the one in South India. And also it might so happen that if the conditions is representing or corresponding to a much lower temperature pressure conditions, and there like if the chemistry is such that you have bicarbonate and the pH of the fluid is somehow is decreasing, or in a way that the condition is such that you could just get them into CO2 plus H2O, and both being in the pressure temperature conditions corresponding to their one phase liquid stability field, they would both be pure water and carbon dioxide. And then there could be some this is one of the possibilities which could still be put under some questions. Or the other possibility is that they may not be coeval, they may not have been entrapped at the same time, and these have to be very well substantiated by looking at the textural characteristics of the host mineral. If we find that there is no indications of the host mineral undergoing any kind of recrystallization or any recovery from deformation and those kind of features, then the chances that actually we are looking at a situation where they are actually trapped in the lattice of the host mineral as pure carbon dioxide and pure water would remain valid, even though there are many kind of mechanisms which are suggested that because they possibly do have different contact angle with the host solid mineral, but then seeing them occurring together would definitely the observational fact goes that they were definitely entrapped, and if they are entrapped at the same time, then definitely some mechanisms has operated which we are yet to understand. And then and we have during the time of our application discussion and application to metamorphic rocks, we also discussed about the conditions or the proposition of recrystallized primary inclusions, where it is suggested that originally trapped homogeneous aqueous carbonic inclusion during the recrystallization of the host mineral gets split up into aqueous component and carbonic component, and because of their difference in their contact angle, carbon dioxide being obtuse and water being acute, water percolates through the grain boundaries, whereas the carbon dioxide is actually entrapped within the interior of the grain. But we do see innumerable such instances where the carbonic inclusion and the aqueous inclusions are entrapped within the interior of the host mineral grain itself. The other issue is that homogeneous versus heterogeneous entrapment. It has been there has been quite a lot of discussion which have been made on this particular issue, that there are possibilities that the inclusion actually, that means our basic assumption is violated. The basic assumption of homogeneous entrapment, that means the fluid at the time of entrapment was a homogeneous fluid, is sometimes suspected. That means if, although we know that we do have very well defined regions of immiscibility or inhomogeneity, means if there are possibilities of inhomogeneous entrapment, they can only happen, suppose in the context of a pure water or a water plus electrolyte, water plus NaCl or any other electrolyte mixture, where this kind of relationship remains very simple only with the changing of the critical point or the position of the liquid vapor homogeneous equilibrium curve or the boiling curve. So, we know that the only possibility where such an inhomogeneous entrapment is possible is very specific conditions corresponding to the boiling condition. Otherwise, we have the entire vast field of pressure and temperature in which we get the wall of the aqueous fluid as one phase, similarly in the vapor. So, if at all there is a possibility of entrapment of the inhomogeneous entrapment, suppose for example, if an entrapment is taking place somewhere here and there is both liquid and vapor present during the growth of the mineral. So, that means when a mineral is growing, there are bubbles along with the liquid water, and when the crystal is growing, so it will entrap a mixture of liquid and vapor instead of entrapping either a liquid or a vapor. Means we have discussed situations where we believe that there are coexistence of liquid rich and vapor rich inclusions in the same host mineral grain, same grain of the host mineral, and we presume that the vapor and the liquid were separately entrapped, even though within the same domain, which is basically measuring in terms of few microns in spatial distance. Means whenever we are seeing in a host mineral, there are two inclusions coexisting in the same field of view when we are seeing in the microscope, then these two inclusions are just about a few tens of microns apart, and when they are growing in nature in any regime in which the mineral is precipitating, then the situation would be such that the entrapment would give rise to a situation where in one case a vapor is entrapped and the other case a liquid is entrapped, and that basically will give us a situation which will be interpreted as a boiling condition. But in contrast to that, we are considering a situation where the inclusion is trapped, taking a part liquid and a little bit of part of vapor. Now, in that case the basic assumption is violated, and if we go for heating this particular inclusion in a homogenization run, then the value of the temperature of homogenization that we get is actually not the condition of entrapment. So, that has been the main important point of suspicion, and many people have tried to demonstrate that where one could possibly suspect such kind of an inhomogeneous entrapment by giving us idea that, well, if the histogram of the temperature of homogenization is observed, then it might be that it could possibly show some spreads instead of normally if we see for example, it could be a very simple case of a unimodal distribution in the temperature of homogenization, in which case possibly we will say that okay, it's a there has not been any inhomogeneous entrapment, or there has not been any re-equilibration or disturbance to the inclusions after they are entrapped. But if we get some situation like sometimes the temperature range that is observed in the homogenization, the range which is observed in the temperature of homogenization is too wide, or sometimes even having some bimodal kind of distribution, either positively or sometimes negatively positively skewed or negatively skewed. Mostly it is positively skewed. Then it is interpreted that it may be due to because of inhomogeneous entrapment rather than homogeneous entrapment. So, these have to be very carefully sort of interpreted, and they should be from the very beginning of the study of the fluid inclusions, the petrography and the consistency in the microthermometric data. And there must be enough reasons. There are many explanations which are provided for that. So, that is the situation sometimes which one has to be careful. And the immiscibility regime, that as I have discussed, whether it is a if it is water, then we have to look into where we are. If we get some such situation, that means the situation will be such that there will not be any vapor phase homogenization, but the temperature of homogenization is actually having a spread. But one thing has to be very clearly remembered here, that when we are looking at this situation, any kind of inhomogeneous entrapment, if we are looking at the same sample or the same host mineral grain, if we get such kind of a distribution, then it could possibly a thought would possibly be go in that direction. Otherwise, when we are compiling the microthermometric data so for example, we are examining an entire ore body in its strike and the strike length and whatever depth that we have been able to sample, and we are measuring inclusions in scores of such samples and in measuring them in hundreds or thousands in number. There the spread is of course very expected, and there are explanations, because there could be many several stages. For example, if we look at the fluid inclusion data generated in many of the magmatic hydrothermal systems, we get a complete range of temperature of homogenization of the fluid inclusions going to temperatures above 700 degrees centigrade to coming to temperatures corresponding to even just 150 to 200 degrees Celsius. In those conditions, we know that yes, they represent they are actually the manifestation of an evolution of a magmatic hydrothermal system from a very high temperature and high saline stage to a very low temperature, low salinity stage, and in those kind of cases they are very clear. But one thing possibly could be kept as a point of notion, as a note of caution, that if we get some such kind of a spread within the single minerals, the very simple sample, or within the same grain, or just a few neighboring grains within the same host mineral, then this kind of the interpretations could possibly be made with some caution and keeping this in mind. And then the non-isochoric path, the re-equilibration and compositional change in inclusions, which is also sometimes looked to be the issue when we come to the interpretation of our microthermometric data, because non-isochoric path has been shown as isothermal decompression or isobaric heating or isothermal loading kind of situations, and the textural modification of the inclusions which we discussed. In such kind of situation also we have seen that if it is an isothermal decompression or isobaric heating, then the inclusion undergoes some kind of explosion texture, and there is a redistribution of the temperature of homogenization as to what would have been the case if the inclusions would not have been disturbed. So, these are the situations which also need to be resolved, because in many of the situations we see that it is a function of the inclusion size. There is a very good exponential relationship which is established, that the extent or the magnitude of the internal overpressure that is exerted on the inclusion on the wall of the host mineral and the yield strength of the mineral and the pressure that will be exerted by such kind of non-isochoric path. And so we have seen that the larger and the irregular shaped inclusions are more likely to get destroyed or to have undergone such kind of plastic deformation of the inclusion cavity, or even sometimes brittle deformation of the inclusion cavity. But a careful petrography and textural observation of the sample would definitely help us in to overcome such kind of situations. Then necking down of fluid inclusions. Here that is what I just took this diagram. This diagram has been taken, which is also present there in the one of the chapters by Edwin Reuter in the book Geochemistry of Hydrothermal Deposits. So, what is portrayed here is that it is a kind of necking down of the inclusion, which might result in this kind of end. This could be the end result of necking down process. If this is an original inclusion which is trapped at temperature of trapping, it might so happen that if they are necking down, then they might end up in situations corresponding to A, B and C, where the inclusion A would homogenize at temperature which is greater than temperature of trapping. Inclusion B would be homogenized between T1 and T2, and inclusion C to be in T2 and T3. These kind of propositions which I made earlier also need very careful examination, and in this context that is what just I have taken this image from one of the papers that was published in 1968. The title of the paper says that experimental evidence that fluid inclusions do not leak. So, this was shown as maybe that many of the natural inclusions were subjected to higher pressure and temperature conditions, and the observation was that most of the inclusions remain intact, and few of the inclusions, even sometimes where some kind of brittle fracturing was observed, was ascribed to that leakage due to micro cracks during sample preparation. Even this kind of things are also suspected at some point of time, but this could possibly be somehow taken care of, because if the process or exactly the process that we adopt for preparation of the sample, we have taken enough care so that the samples are not actually affected, because these days there are very precision cutting equipment where the inclusion, where the sample could be cut to very thin slices, and the thinning and the polishing could be done in such a way that the sample remains intact and there is no external damage that is done to the sample. But on top of it, if we look at this kind of diagrams very critically, we find that it may not be the case all the time, just as been inferred by these workers before. That if this temperature of trapping has taken place at a temperature which is definitely higher, and after that if this inclusion is present initially as a liquid plus vapor, if it is a pure aqueous inclusion which is trapped at T T, now at temperature of T1 it has given rise to a vapor, means it is already corresponding to conditions which is on its liquid vapor equilibrium curve, and we know that they must be of pressure which is below 220 bars and temperature which is well below 370. If it is containing little bit of salt, then it may be just been higher by a few degrees or a few tens of bars, and in those kind of situations also bringing about the inclusion deformation is not that very easy. So, these kind of interpretations which have been made could still be examined, and they do give very good petrographic indication, and only thing is that these kind of inclusions could possibly be avoided during the microthermometric run. So, it is not only this, but the results, the experimental results which were discussed for the re-equilibration of the inclusions and deformation of the inclusion cavity, which have got very conspicuous textural manifestation when the sample is being studied during the preliminary petrography work. So, they can always be avoided by taking enough care that such kind of inclusions microthermometric data are not actually considered under normal circumstances, unless it becomes very essential, or when it only we are talking about deciphering the conditions in which the sample underwent some deformation or later re-equilibration process. If that is what is actually in our mind to work out, then only we will be considering the data of these inclusions. But if our objective is to work out the characteristic of the parent fluid and the conditions of formation of the rock under that kind of an environment, then these inclusion data will not be helpful to us. Okay, then some of the quick questions. How to differentiate between pseudo secondary and secondary inclusions when the sample contains trail bound inclusions. So, it possibly is a good is a relevant question to consider. If there are only trail bound inclusions, that the only difference that we know that we know that the difference that we if there are many grains of the host mineral which is present there, then we know that there are the cracks which are transgranular and the inclusions which are trapped within these or present within these transgranular cracks, which are the micro cracks. They are the ones which are unequivocally interpreted to be secondary, or the cracks which are generated after the formation of the host mineral. So, they are the secondary inclusions. And in contrast to that, when we have lots of such grains of that particular inclusion, and we see that there are only fractures which are within the mineral grain themselves and are not extending to the grain boundary or not crossing through or transgressing through the grain boundaries, and there are inclusions within these, then they are the ones which we consider them to be pseudo secondary. So, pseudo secondary is essentially primary, so they are essentially they are formed during the process of primary growth of this mineral. Now, but then little bit of thought has to be given to it, because it might so happen. So, one of the situation is that if in one polycrystalline aggregate of a single mineral host like quartz, we just see a very stray occurrence of such kind of a fracture of the heel crack only within a just about a single grain of the host mineral is showing that. So, in that case it could be suspected that it is just a case where the a fracture which was actually transgranular has just terminated in one grain, and that may not actually be a pseudo secondary trail. So, in order to interpret a particular trail to be secondary, to be pseudo secondary, it needs to be consistently be present in. So, the only point that I could possibly make here is that in order that this in order that this particular heel crack, the inclusions which are present in that heel crack to be taken as pseudo secondary, such kind of heel cracks should be present in more than one such grain of the host mineral. That could possibly be one of the ready answer that can be given in this context. So, is there any constraints regarding the shape and size of primary inclusions? If yes, is it applicable to secondary fluid inclusions? As far as my experience goes of working for so long a time on fluid inclusions and looking at many diverse types of samples from different geological terrains, I really do not establish any relationship between the size of the shape of the inclusions and its origin being primary or secondary. There are propositions that the inclusions re-equilibrate or even put, for example, in a isothermal loading kind of situation, or even the inclusions were subjected to hydrostatic pressure condition, the irregular shaped inclusions tend to become more like negative shaped shape or more regular. Whereas, because in some of the photographs which I saw in the very introductory part of the lecture series, where we saw that minerals like halite or anhydrite, they do have such dense population, the extreme, I mean the populations, almost every inclusion present in that host mineral is of negative crystal shape. So, there is some control being exerted by the inherent the nature of the crystal, where the mineral, where the fluid is being entrapped. Other than that, there is sometimes it is told that in the heel cracks the inclusions or the secondary inclusions tend to attain for to a negative crystal regular shape, but these kind of conclusions are very oversimplistic. So, is petrography essentially required before microthermometry? Why can't it be done simultaneously with microthermometry? This is actually, the answer is a very strong yes, that petrography needs to be done before microthermometry. Even I would go on to suggest, if the facility is available, then every sample which is being intended to be studied for fluid inclusion first need to be prepared as a normal thin section of a 30 micron thickness, so that the textural characteristic of the host mineral can be known beforehand. So, how much of recrystallization has taken place, what kind of deformation features like presence of undulose extinction, in the host quartz grain. These kind of features could very well be studied beforehand, before a thick section or a wafer is prepared for the same sample, prepared from the same sample, and the fluid inclusions are examined. And a thorough petrographic study with different inclusion types, the kind of domain in which they are present, either in the interior of the grain or in the grain boundary or on the, and all these kind of features, whether the quartz shows some growth zones, primary growth zones, all these things will be very clear once the petrography is done. So, petrography, fluid inclusion petrography is a must before microthermometry. So, trying to classify inclusion or to do petrography while doing microthermometry will be very time consuming and also a difficult process. Now, should secondary inclusions be subjected to microthermometry? The answer is again it depends on the problem that we are actually addressing, because sometimes we see that even the heel cracks there are inclusions, mixed aqueous carbonic inclusions, which generally the entrapment process takes place at higher pressure and temperature conditions. So, generally it cannot be very well generalized that all the secondary inclusions are entrapped at temperature pressure conditions which are very low or more superficial near surface conditions. As you have seen in many metamorphic minerals, where in minerals like garnet or pyroxene there are secondary inclusion trails, and but so even sometimes it would be very, even if we are looking at a hydrothermal ore deposit, and it is always better to get an idea about the nature of the fluid that were entrapped as secondary inclusions, so that to decide whether they should also be integrated into the data to talk about the fluid which actually were responsible or which who came to play any time afterwards for any enrichment or any process that took place afterwards. So, the three modes of what are the physical significance of the three modes of homogenization of aqueous fluid inclusions, liquid and vapor. As we know that liquid and vapor inclusions, the homogenization, if they occur in coeval inclusions, they are of much important implications like deciphering boiling. Critical homogenization has no much of any greater significance than just the conditions corresponding to the that critical temperature of the fluid of that corresponding weight percent of the electrolyte that is present. Why other salt species are not considered for the aqueous inclusion? We need to wait for more better PVTX relationships be established, so that we would possibly not have to express the salinity as weight percent NaCl equivalent. We will be able to express the salinity in definite terms of what exactly the weight percent of NaCl or KCl or CaCl2, but we have to wait till we reach that particular. So, as I have said that fluid inclusion study, there are lots of areas in which lots of more work and development need to be done. So, metastability, what is metastability and how to get rid of it? Metastability is the lack of response of the inclusions to heating freezing cycles. For example, the inclusion does not freeze even if cooled to a temperature of almost minus 200, does not homogenize, or even after the homogenization the vapor bubble does not come back, and if or dissolution of a daughter crystal, actually the daughter crystal does not again reappear on cooling. So many situations could be there, all corresponding to metastability. Sometimes the metastability is taken care of by repetitive cycles of heating and freezing. Say for example, in one by aqueous biphase inclusion, the temperature of homogenization occurred at 200 degrees Celsius, but then when the temperature is cooled down to almost like even room temperature, the vapor bubble does not reappear. So, even if we freeze the inclusion and the vapor bubble comes back at a temperature much lower, sub-zero temperature, and again when we heat it, if we are able to reproduce the temperature of homogenization, then there is no problem, we can always take that homogenization temperature data. But if it homogenizes at temperatures way different from what was the original value, then we know that we are not able to reproduce the temperature of homogenization, and in that case that inclusion has to be simply discarded. And metastability does not depend on salinity, but metastability does depend a lot on the inclusion size. So, that is why we generally avoid inclusions which are less than 5 microns in its maximum dimension. So, the implication of statistical analysis of fluid inclusion data, how one can set the number of fluid inclusions to be studied per sample. This is a question on which no direct or straight answer is given. So, that is definitely fluid inclusion data is definitely quantity intensive. So, the number of data has to be good enough so that it takes care of the statistics in terms of the distribution in temperature of homogenization or the salinity or whatever parameter. And sometimes the question as to how many inclusions to be studied per sample. So, we do have to believe or take the thing as a random sampling. If we are taking a sample depending on what is the population, if the inclusions are very scarce or very in the sample, then definitely the number has to be low, but the inclusions are a lot. So, in that case we have to see to it that we have to convince ourselves that we have done a random sampling, and sometimes the inclusions occurring in cluster and group do have very close values of salinity and temperature of homogenization. So, in that case taking more data would not be a problem, but sometimes their temperature, homogenization and salinity are widely different. So, sometimes that becomes a little more time taking to take all the data, but it should be, we should convince ourselves that we have made a random sampling and have taken adequate sample. So, captive phase, do captive phases have any significance compared to daughter phase? So, captive phases are the ones which are called the accidental phases, which are which did not precipitate from the inclusion fluid, but were trapped along with the liquid within the cavity. So, they do not have much of significance, but sometimes if a halite is an accidental phase and it still gives a dissolution temperature, then the salinity would be overestimated, but in that case this situation could be overcome by looking at the population, because if the fluid was at a certain point of time had a certain value of the salinity, then there should be more than one inclusion which should be polyphase at room temperature. If we are only getting a stray inclusion in a population which is polyphase and rest all are biphase, then the suspicion that this daughter phase is the halite that is there is not a daughter phase but a captive phase would be stronger. So, how can one understand liquid immiscibility during fluid inclusion study? So, the questions of boiling as well as the unmixing in aqueous carbonic fluid has been discussed. Reproducibility in freezing to plus minus 0.1 while heating is plus minus 1, why is it allowed? So, we know that salinity value will vary significantly if the range is more than that, and that is also we cannot have lower reproducibility than 0.1 in freezing cycles, whereas in a calculation of density a difference of temperature of 1 is not going to make the density change even in the fourth place of decimal. So, that is why a plus minus 0.1 is allowed. In a sample there are hundreds of inclusions. What is the basis of choice of inclusion for further study? So, naturally we first go to look at the inclusions, workable inclusions in terms of their size and also the shape, the regular shaped ones. They are going to give us dependable data. So, that could be only the criteria for choice of these inclusions. Sometimes if the inclusion population is so low that we are not actually left with much of choice and we have to take the data on as many inclusions as possible. How can one relate the data after fluid inclusion study to fluid before trapping? So, that is actually the isochore and the correction for the pressure correction which comes next. What is pressure correction and is it strictly related to pressure? It is actually not related to pressure, but depends on the isochore, the steepness or the gentle the slope of the isochore, and if we have any other independent estimate of the temperature or pressure, the isochore helps us in getting the value. So, TM clathrate, why TM clathrate is considered instead of TM H2CO2 inclusions? We know that because most of the a lot of water molecule is taken up by carbon dioxide to form the clathrate by increasing the salinity apparently. So, TM clathrate will only be used for measurement of salinity. H2CO2 inclusions are more susceptible to leakage because the building up of internal pressure which yields which exceeds the yield strength of the host mineral. So, what is the basis to choose the inclusion to draw isochores? Only when we get coeval inclusions and we know that there could be chances of getting the intersection of the isochores, that it is always advisable to draw the isochores. Otherwise also, like some of the examples which we have shown for application to structural geology, there the isochores need to be drawn in terms of what could the maximum and the minimum slope value we get from the microthermometric data. At that point of time we know that represent the range. So, the maximum possible range variation in temperature and pressure. So, the isochores need to be drawn. In a sample where all types of inclusions are present, how should we proceed during the microthermometry? As it also I told this point in the introductory session that you should better to go for the pure carbonic inclusion first, freezing, followed by the freezing of the aqueous carbonic inclusion to take data for the carbonic component, then go on to relocate the aqueous, then the aqueous biphase inclusion salinity, then relocate them to get the temperature of homogenization, then go on to the aqueous carbonic inclusions to take their final homogenization temperature, because most of the cases they might leak, and they may also make the other aqueous inclusions leak because the temperature is high. So, often there is use of the word gas to describe carbonic or aqueous carbonic inclusions. It's possibly it's not that very correct, because they are not present in the gaseous form. We can see them very clearly, they present in the liquid form and with the pressure corresponding to the liquid vapor equilibrium. So, it is advisable to be an expert in any one area of geology with expertise in fluid inclusion, and to collaborate with experts of other disciplines, not just to increase the productivity, just to also to contribute to science. So, collaboration with other experts, being a fluid inclusion expert is always more advisable, and definitely makes a very good better combination. So, one should be aware of all the shortcomings and limitations of fluid inclusion, because no single methodology can give all the answers to the problem that we pose in terms of the geological problem. The situation that you are dealing with may be very specific and needs a very thorough reasoning and interpretation of your own results, provided your observation is right. So, in this case you need not have to be same or exactly identical to what you get in some other locality, because your situation may be very specific and unique. The only thing is that you have to take enough care that you have your data, the observations are right, because it is sometimes said that wrong interpretation is something on which the science survives, but actual wrong observation actually is damaging to science. So, fluid inclusion is time consuming, is painstaking, but it's finally at the end of it is rewarding and satisfying endeavor. And as we know, there is a lot more of work to be done to make this particular field even much more useful, and they definitely want to look for the day that fluid inclusions are able to be utilized to solve geological problems in much bigger way. So, thanks a lot, and all those who have registered for the writing the final end semester exam and examination at the end of this particular course, all the best wishes to them. Thank you.